Section 20.7, parallel wiring. Parallel wiring means that the devices are connected in such a way that the same voltage is applied across each device. So you can imagine if you have two resistors, you're connecting each of them directly to the terminals of the battery. So R1 is connected directly to the positive and negative terminals. R2 is also connected directly to the positive and negative terminals. Now in practice, it's a pain to try and draw them connected right to the battery like this. So rather than drawing it like this, the same circuit can be drawn as shown below, where you have the battery and a wire coming out of it. Think of it as extending the terminal, and then that is split into a wire going through R2 and another wire going through R1. It then comes back together into a single wire going back through the battery. So we can see, unlike the series wiring, there's no one path to go from terminal to terminal, right? We have to choose. Either we go through resistor 1 and back to the battery, or we go through resistor 2 and back to the battery. And so as a result, each of these resistors will receive current from the battery as though the other one isn't present. That means that when we have two resistors connected in parallel, they're going to draw more current than either resistor by itself, because each one wants to get all the current, or as much as it can. So some examples of parallel wiring are the households are often wired in parallel. Right? So here we have the 120 volt generator and AC generator, and it comes to the house, and there are all these different outlets. And if these outlets were all wired in series, then in order to turn on the TV, you'd also have to turn on the light, right? Because they would all need to be on. The stereo would need to turn on too. But because they're wired in parallel, the TV is able to connect to the generator, to the electricity, as is the stereo and the light bulb with its switch. So each of these can operate at the same time, but they don't have to because they are wired in parallel. Now, when things are wired in parallel, you can think back to our water pump analogy. And so the pump is our battery or AC generator again, right? That's creating the flow of charges. And the two parallel pipe sections, like parallel wiring, are equivalent to a single pipe of the same length and same total cross-sectional area. So it's like the water splits into the two, but we could imagine it just staying as one that's super thick. And that's what we're going to be trying to do when we create an equivalent circuit for parallel wiring. So let's work towards how we can create a equivalent circuit for parallel setup. So when we have the parallel circuit set up, we know that the total current that's coming out of the battery is going to have to be equal to the current that goes through R1 plus the current that goes through R2. That current splits. So I is equal to I1 plus I2. We can then write the currents in terms of the voltage and the resistance. So V divided by R1 plus V divided by R2. Now we remember both of these are feeling the full voltage of the battery. So the V doesn't have a subscript here because they are wired in parallel. The R's still do. They are different, the currents are different. Because the V is the same, we can factor it out so that we have V times the quantity 1 over R1 plus 1 over R2. We're going to call this in parentheses R1 over RP. And this gives us the rule for finding the equivalent resistance with a parallel wiring, that 1 over the equivalent resistance, RP, is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus, and so on and so forth. This is a little more obnoxious to calculate than the series wiring, but as long as you follow the math rules, you should be okay with it. It's a very solid rule to fall back on. And this will then allow us to write the circuit as just a single resistor with RP as its resistance. Let's check an example of this. Example 10, main and remote stereo speakers. Most receivers allow the user to connect to remote speakers in addition to the main speakers. At the instant represented in the picture, the voltage across the speakers is 6 volts. Determine A, the equivalent resistance of the two speakers, B, the total current supplied by the receiver, C, the current in each speaker, and D, the power dissipated in each speaker. Right, so that's a number of things to go through. The key here is these speakers are wired in parallel so that you can use them at the same time or one or the other. Gives you more options. So let's start by solving for the equivalent resistance of the two speakers wired in parallel that are noted in the picture. R2 is 4 ohms, R1 is 8 ohms. So if we draw a circuit diagram for this, we could have our AC generator that is 6 volts connected to R1 of 8 ohms, R2 of 4 ohms, and we want to get to an equivalent circuit that's just one resistor. So we can note that 1 over Rp is equal to 1 over 8 ohms plus 1 over 4 ohms. Now if we add this together, we'd find that it's equal to 3 over 8 ohms, or you can work just with the decimals. You don't need to keep it in fraction form. But the 3 over 8 ohms is not the resistance. To get to Rp, we need to take the inverse of both sides. Right? So we need to take the inverse of Rp and take the inverse of 3 over 8. In other words, 8/3. If you calculate 8/3, then you'll get the proper 2.67 ohms. And one clue that you haven't yet inversed it is if your ohms appear in the denominator. That's not the right units of resistance. So that's a sign that you do need to invert it. Right, so there's the first part. Now we want to find the total current supplied by the receiver and the current in each speaker. So if we want to do that, now that we have a simple circuit, we know the total resistance and the voltage at that instant, we can figure out the current. So our current is just going to be the voltage divided by the total resistance in the circuit. So 6 volts divided by 2.67 ohms, which comes out to 2.25 amps. The current in each speaker is going to be the same equation with the same voltage because we're in parallel. The only part that will change is the resistance, if it's 8 ohms or 4 ohms. And sure enough, the current is less in each of the speakers, in speaker 1 and speaker 2. But if you add these together, you'll find that they come out to 2.25 amps. So that matches what we'd expect. Right, and then if we want to find the power dissipated by each of the speakers, how much power are they sucking? It's going to be the current times the voltage. So we can take those current values that we just calculated times the voltage, which we know is the same for each of them, and we get 4.5 watts for the first one and 9 watts for the second one. So that shows you some basic calculations using this parallel wiring. Let's check one more example, a conceptual example of a three-way light bulb in parallel wiring. Three-way light bulbs are popular because they can provide 3 levels of illumination. Within the bulb, there are 2 separate filaments. When one burns out, the bulb can produce only 1 level of illumination, but not the highest. So are the filaments connected in series or parallel? And how can 2 filaments be used to produce 3 different illumination levels? I want you to think about this before you move on, so go ahead and pause the video. Okay, hoping you did that. Well, if we think of this, this is going to be another example where we need to have them in parallel. Because if they're in parallel, then we can use one filament, the other filament, or both filaments together. So here's a schematic where we could have switch A thrown to pass it through the 50-watt filament, or switch B thrown to pass the current through the 100-watt filament, or both of them thrown so that we have current passing through both of them, which will be the very brightest. So this is a simplified schematic of it, but it hopefully gives you some idea of yet another advantage of parallel wiring. You might also think of your Christmas lights. If you've ever gotten some really old Christmas lights and a single bulb goes out, you'd be sad because sure enough, those were wired in series. So one bulb goes out, the whole string goes out. Nowadays, they're often wired in parallel. So if you lose a bulb, the rest of the strand stays lit, and there is much rejoicing.